Dear students, before every chapter, we would discuss certain concepts of mathematics that will be used in that particular chapter. Since this particular class is interdisciplinary in nature, there would be some students who may struggle with some of the concepts of mathematics. So before start of every lecture, I will follow the same practice. In case you find some of these concepts to be simple or you have read this before, feel free to fast forward or skip this video. Okay, so here let us start with some of the basic concepts of probability that we would use time and again throughout this course of network science and specifically in chapter 2. So whenever we talk about probability, the first word that comes to our mind is something called as random variable. So when we talk about random variable or RVs, we are talking about variables where outcome depends on some random phenomena. For example, tossing of a coin, it's completely random and probability of getting a head is 1 by 2 and probability of getting tail is 1 by 2. So there is some randomness associated. You're never sure of whether you are going to get a head or tail. So why we care about probability in the context of network science? As I mentioned in my introductory lecture, that in network science, we would be dealing with real world systems. And it does not matter how great our sampling technologies are. We would always be dealing with something called as finite data, which would constitute the sample and it will represent the population. So population is entirety, that is what truly exists. However, in real world scenarios, we in most of the cases we never get to see a population and we always deal with samples. Then we look into the samples, the statistics of these samples. For example, we look at their mean, we look at their variance, we look at their median, or we look at mode, or even we look at sometimes the higher order moments which are called as, let us say, skewness, kurtosis, and so on. So we'll not worry too much in the context of this what this skewness or kurtosis are, but just so you know that these are ways to draw the inference about the population by looking at the samples. So even in network science, we are dealing with always a sample of nodes and edges that would constitute the entire population or complete set of the network. For example, let us say that we are working on social networks. We are sampling that how humans are interacting, and it would be virtually impossible for us to know for all population that we are targeting that who is interacting with whom and so on. That's why we have to deal with samples in this case. So let us try to formalize it a little bit mathematically. Let us say that we denote this x as a random variable. So in this case, x is our random variable which can take some values. So x can be equal to x1 or x can be equal to x2 and x can be equal to xn and so on. So we are interested to determine what is the probability that this x takes a certain value xi, and if we have n observations and we see that in this n observation x take value of 1 maybe 10 times and x takes value of 2 5 times, then just by looking at this, if I ask you that what is the probability that x would be equal to 1, you would simply say that we know that x equal to 1 happened 10 times out of n observation. So the probability that x takes a value of 1 is equal to 10 by n. So we would deal something with called as degrees of the nodes, and this will become more clear what this degrees means. So do not worry about the technical cliches that I would be using, but let us say that we denote this degree by k. Then if somebody asks us that you have observed n nodes in your network and out of that you see that some k samples have value equal to x. If somebody asks us what is the probability that x equal to x, you would simply say that it is k divided by n. We also denote this as probability that a particular node would have a degree equal to k as pk, and we say that in this case instead of x we are interested in how many nodes have degrees equal to k divided by total number of nodes that we would have in our network. So this would essentially represent what is the probability of observing a particular degree node in a given network, and this will form foundation stone for all the discussions that we are going to have when we go to the details of network analysis. Now this pk is often referred as probability mass function. So there is a distinction between mass function and density function, and I will shortly talk about that. So in mass function, we say that only discrete values of k's are permitted. For example, if we are talking about a social network, and I gave this example of Saddam Hussein in last lecture. So Saddam Hussein may have 3 connections, 4 connections, and n connections. There is nothing like 2.5 connections or 2.75 connections. So we are always talking about discrete values here. That's why when we plot this, that is on x-axis, if we have the value of probability, and on y-axis we have value of probability, and here we have the associated k, we would get a plot something like this. That is, if this look like there is some mass concentrated on top of this column, and hence the name probability mass function. As you can imagine, in network science, probability mass functions would be typically used. However, why we are using this word function? So let's try to understand that. For mathematical convenience, we want a generic expression. That is, can we write it in a form of a neat mathematical formulae, so that if we have to do some summation or some integration later on, that becomes easier. So I will again give you a very simple example just as a motivating case, so that you can understand this, that how a mathematical convenience comes in. Let us say in the coin toss example, we say that heads is represented by 1 and tails is represented by 0, and you know that if coin is unbiased, the probability of getting heads as is 1 by 2, and probability of getting tails is also 1 by 2. Now if I ask you, can you give one single mathematical expression that is probability of x equal to small x, what that would be? Now you can smartly write this as p to the power x. If you say that head is denoted by 1 and tail is denoted by 0, probability of x 1 minus p 1 minus x. Now if you put value of, let us say that what is the probability of x equal to 1, what you would do, 1 by 2, x equal to 1, 1 minus p, and x is equal to 1 will render this term as ineffective, or something raised to power 0 is equal to 1. So you get probability of x equal to 1. Now if I have to write probability of x equal to 0, similarly you can write probability of 0 1 minus p 1 minus 0. Now this particular term would be rendered ineffective, so this would be 1 minus p, that is probability of not getting a head, and this simply again is 1 by 2. Now if you see here, this was a very simple example where probabilities are equal. Let us say that we have some example where probability of having a head is not, it's a biased coin, so instead of 1 by 2 we are dealing with something like 3 by 4, and hence probability of getting tail would be 1 by 4. Now all you have to do is keep focused on this formula, plug in these values, and you can keep on changing these values and get a behavior that how the probabilities of getting heads, one head, multiple heads would change if we put them into a form of a combinatorics expression. So these expressions that we get by looking these things from a different perspectives, these are called as functions. That is, you are expressing it in form of a mathematical entity, and we call them as a probability mass function, and they have some specific names. For example, the function that I wrote here, it is called as Bernoulli's distribution. And when we talk about Bernoulli's distribution, we are just talking about one single trial. That is, you are having one coin, you tossed it, you got an outcome, and so on. However, when you expand this to multiple trials, this becomes the binomial distribution. So again, in this particular class, we would be concerned about understanding these distributions intuitively, and we would not worry about all the distributions that exist. But if you're interested, there is a very good book on statistics by Montgomery and Runger. I will post its link in the description. So I would advise that you should take a closer look if you are really interested into subject of mathematics. But for this particular chapter, I would say that if you understand why we are writing this in this form, that would make perfect sense for the upcoming concepts. Now, what is the reason we are writing them in some mathematical form? Because we are always interested in some calculation of something called as expected value of a random variable. Now, what is an expected value? You go to a lottery shop and you want to purchase a lottery. So, and this lottery is again simple heads and tails, that you go and you pay rupees 100 and they will toss a coin. If you get a head, you pay rupees 100. If you get a head, the reward is rupees 100, let us say. And if tail comes up, you lose rupees 200. So if it head comes, you are plus 100, and if tail comes, you are down minus 200. Now, if I ask you that should you go for this particular lottery, you intuitively know that no, I should not go it, because chances of losing are much higher than chances of winning. But when we try to put it in a mathematical perspective, what you would say that my expected return in this case is equal to what is the chance of getting head, which is half a times you will get head, and what is the associated gain is rupees 100, and what are the chances that you will get tails is 1 by 2 times 200. So your expected return in this case is 50 minus 100, which is minus 50. So you are starting this experiment where you are already on losing side, and the expected value is that if you play this game enough number of times, you may lose 50 rupees on an average in each try. So now if you look at, you could be lucky one off time, that is you go there and you get a heads first time, you get rupees 100 and you come out. That's where we are not talking about the specific outcome, we are talking about expected value of the return, where the probability is looked from the and the probability is established from the multiple trials of that experiment which has already taken place. Now if you put this into perspective, here the event has only two outcomes, heads and tails. But in real world or even in network science, we would be dealing with vectors, that is x can take value of x1, x2 and so on up to xn. And now if I ask you to calculate what is the expected value of x, it would be tedious for you if you work outside the mathematical framework. So what we say that expected value of x is simply xi pxi and its summation from minus infinity to infinity, because you say that now does not matter whatever value xi takes, this should be multiplied what is the probability of observing that particular x, so that your expression is complete. Now in case of network science, we would be often dealing with the degrees. That means degrees cannot be negative, and hence we can say that it can vary from 0 to infinity, ki pki, and this would be the expected value of degree of a node. On an average, if you take any node from your network, the expected degree or the average degree of that particular network can be established as 0 to infinity ki pki. And you can imagine that not all nodes will have exactly same degrees. There would be some nodes which have almost no connections, and there would be some nodes which would have very high number of connections. So this just represents the mean behavior or average behavior, and that is exactly why this is called as mean of a random variable. And in this case, it can be written as 0 to infinity ki pki. Similarly, you can define some higher order expectations, that if somebody asks you what is expectation of k square, all you have to do is that write the same expression. Again, we will not worry about the negative numbers. We will simply say that it is k square pki, and for each I varies from 0 to infinity ki square pki. So this is an example of a discrete case. There is just for sake of completeness, let us also discuss the case of continuum. Let us say that we are living in some magical world and these degrees can be fractional also, and that is they can be 2, 2.1, 2.2, 2.4 and so on. Then this summation would be a tedious task. And let us say that this x now, instead of just belonging to z positives or positive integers, it belongs to the domain of x is real. Now we are interested to determine what is the probability of x taking value between x1 and x2. Now summation, you know that when we are talking about discrete variables, it's always easy to summate them. However, when we are talking about some continuous functions which look like this, the integration would be a better way to do this summation in continuum. Hence we simply say that it's not a problem. Let us replace this summation by the integral, and we take from x1 to x2, and we will use the probability of k and summate it over dk. So if this is k and this is probability of k, this is our, we call this as probability density function. Now for a function to qualify for a PDF, there is another condition that it should always meet, that is from minus infinity to infinity, probability of x, I'll not confuse you with k and x, probability of k dk should be equal to 1. And as you know that probabilities cannot exceed 1, and whenever you look at the total probabilities, that should also submit to 1 in the real domain. Now we have looked into some PDFs, and the question would arise that what are the functional forms, what I should integrate. So to do integration, I need to know some mathematical form of this pk, and even if I have to summate, I need to know what is pki. So if this is continuous and this is discrete, and to avoid any confusion, we will denote this by fk, and we will use pk for denoting the discrete variables. So there are some well-known distributions. For example, normal distribution is an example of continuous distribution. We will learn something called as power law when we go to chapter 4 or module 4 in our discussions. Similarly, we already saw an example of discrete distribution, which was Bernoulli distribution, which is used to model Bernoulli trials where only two outcomes are possible. Similarly, we also talked about something called as binomial distribution, which are used to model multiple binomial trials happening in an experiment. Similarly, power law can be also used to describe discrete variables. So this would be power law distribution, again, which we will cover in next chapter. Now with this introduction, as far as you understand why do we need probabilities, that is, we are always dealing with samples. What is an expected value? Expected value is nothing but it's a weighted average where weight is assigned by the probability of occurrence of that particular instance and summating over all possible values, and coin toss is always a best example to keep visualizations strong. Finally, we would be dealing with some matrices. As I mentioned in the sort of a prerequisites, that you should have some basic understanding of matrix algebra, because we would be dealing with something called as adjacency matrix, and this adjacency matrix would make our life easier when we would work on computer as well as try to get some expressions for basic statistics of networks. So adjacency matrix would be denoted by A, and matrix, as you know, is a collection of numbers arranged in some square or rectangular form, and adjacency matrix has one special beauty, that it is always a square matrix of size n cross n, and here these rows would so number of rows in this case are equal to number of columns, and the identity of each element is given by xij, where I is the number which on what is the row id, what we call as row id, and j in this case would be equal to column id. So for first element, this xij would be x11, and in this case it would be it can be written as xnn, and here it would be x1 and so on. So this is the notation that we are going to stick to. Sometimes you see this typically written A belongs to R to the power m cross n. So this would typically mean that A is a matrix of size m cross n constituting of real numbers. And in case of networks, we will start our discussions with undirected, unweighted networks where x can only take value of either 0 or 1. So x can only be a discrete can only take discrete values of 0. That means if there is no connection, we would say that the entry of this adjacency matrix would be 0, and 1 if there exists a connection between node J and node I. We will talk about the specifics when we introduce adjacency matrix more formally. Now, a quick things that you should look into is that how two matrices are added, how two matrices are multiplied, so that you are somewhat comfortable with matrix algebra. Also, another thing that we would typically use while looking into some of the connectivity properties of networks, we will use something called as basic row operations. Those who are familiar with matrix algebra, they would know that certain operations are permitted without distorting that nature of matrix, that is without changing its rank or without changing its inherent properties. So first property that we look is we can always divide any row by a constant. So for example, if you have row R1 and you want to divide R1 by some constant 5, this is totally permitted in matrix algebra. Similarly, you can also add two rows, that is Ri can be expressed as a new entity Ri, or it can be updated as Ri plus Rj. It would not change the dependence or independence structure of a given matrix. Finally, a very important operation that we will use is swiping or interchanging certain rows. So you can always swap I with J, so Ri can be swapped with Rj and so on. So with this introduction, I think we are good to go and start our exciting discussions of chapter 2, where we will start with a story, try to understand one funny story that how this science of networks or graph theory originated, and how we can do some interesting statistics and mathematics on the real world networks. Looking forward to next lecture. Thank you.